Okay, let us now have the last module of differential equations, which is all about Laplace transform. So for today, let us just discuss the Laplace transform of some elementary functions and their properties. And the next meeting, we will talk on the inverse Laplace transform and applications and how we can use Laplace transform and its inverse in solving differential equations. In the introductory calculus, differential and integral calculus, you learned that differentiation and integration are transforms. This means that roughly speaking, these operations transform a function into another function. In this module, we will discuss the Laplace transform, its properties, as well as how it can be used to solve initial value problems of ordinary differential equation. After completing this module, you are expected to use the definition of Laplace transform to derive the transform of several elementary functions, solve for the Laplace transform of functions using some derived equations, use the operational properties of the Laplace transform in finding transforms of several combined functions, and solve in the initial value problems by applying the Laplace and the inverse Laplace transform. Definition of Laplace transform. So let f, or sometimes we write it as f of t, to be a function defined on the interval t greater than 0, then the integral is called the Laplace transform of f, or f of t, provided that the integral converges. So the Laplace transform, we use this symbol, but I can find the symbol like this in math type. Actually, the is this one, no? This is similar to this one, huh? That is the Laplace transform symbol. So the Laplace of f of t. So the Laplace of f of t is actually derived, or it is defined as the integral of the product of the function f of t and e to the negative st integrated with dt from 0 to infinity. So if you have a certain function, you try to multiply it with e to the negative st and integrate that from 0 to infinity. That is your Laplace transform of that particular function. The name Laplace was named after the French mathematician Pierre Simon Marquis de Laplace, 1749 to 1827. So, uh, but in our class, I will not ask you to derive for the Laplace transform of some elementary functions which are already known. If in case that you forgot yung Laplace transform nung elementary functions, then you can use this definition. Okay? But for now, in our class, I will allow you to use the table of some elementary functions and their Laplace transform. If you want to see the derivation of those in your module of differential equations, some of the derivations are presented there. So you can check on the derivations. But for now, I will not go into derivation, but I will use the table of some elementary functions and their Laplace transform. When the defining integral converges, the result is a function of s. In this lecture, we shall use a lowercase letter to denote the function being transformed and the corresponding capital letter to denote its Laplace transform, which means that the Laplace of f of t would be f of s, the Laplace of g of t is g of s, the Laplace of y of t is y of s. But most of the times we will be using the Laplace of f of t, which is equal to f of s. Let me also introduce to you what is inverse Laplace transform, although we will be taking that in the next meeting. So the inverse of the Laplace is your inverse Laplace transform, which is denoted by the inverse Laplace or the Laplace to the negative 1 of f of s. So when we say Laplace transform, you are given of the function of t, and your Laplace transform would be your f of s. If you are asked to find the inverse Laplace transform, you are given of f of s, and you need to find your f of t. Okay? So that would be for next discussion. For now, we concentrate first on the Laplace transform of a given function f of t, which means that we are to find the integral of e to the negative st times f of t dt evaluated from 0 to infinity, and our result would be a function of s. This is the table that I am telling you, in which these are already presented in most of differential equations and advanced engineering mathematics books. These are some elementary functions and their equivalent Laplace transform. So if you do not want to use this table, then you may use the definition of Laplace transform, wherein on the first column are the function of t. So you multiply it with e to the negative st, and you integrate the product with respect to t from 0 to infinity. And the result would be the Laplace transform or the function of s on the on the second column of this table. What does it mean? If you are asked for the Laplace of 1, that is simply equal to 1 over s. Laplace of t is 1 over s squared. Laplace of t squared is 2 factorial over s cubed. Laplace of t to the n, wherein n is 0, 1, 2 are the counting numbers. You have n factorial over s to the n plus 1, and so on. Take note also that you have here t to the a, wherein a is greater than negative 1. That is equivalent to the gamma function of a plus 1 over a s to the a plus 1. Then you have the Laplace of e to the at, which is equal to 1 over s minus a. Then you have the Laplace of cosine of omega t, which is s over s squared plus omega squared. Sine of omega t, the Laplace of that is omega over s squared plus omega squared. The hyperbolic function of cosine of at is s over s squared minus a squared. The hyperbolic sine of at is equal to a over s squared minus a squared. When I had my face-to-face class or discussion, I asked my students actually to memorize this table, because during examination, I do not allow this table actually to be uh, used as reference during exam. So they need to memorize it. But for now, it's up to you. But it would be better if you memorize this, because we will not be always in virtual discussion or in online platform. So it would be better that you memorize also this table, and for you also to easily solve problems which can be solved by Laplace transform. so that you need not always to look to your table of some elementary functions and their Laplace transform. These are the basic, or as mentioned, some elementary functions. So you should know this and you should memorize for you to easily solve problems on differential equations or any other applications which can be solved by Laplace transform. Madali naman siyang i-memorize kasi ang pagdating dun sa trigonometric and hyperbolic, you should know alin ba yung numerator at alin yung denominator dyan. So pag cosine, it is the S. And pag sine, yung value nung omega, or in the other is A. And then for trigonometric, that would be plus. And for the hyperbolic, you have minus. And then for the Laplace of a constant, that is 1 over S, constant 1. For t is 1 over s squared, and for t squared, you have 2 factorial over s cubed, or you may take the general t to the n, which is n factorial over s to the n plus 1. These are the most common functions that we are going to use, and combinations of them can be encountered in solution of problems in differential equation and others wherein Laplace transform can be used. Okay? Okay. These are some properties of Laplace transform as mentioned in your module. So there are still other properties, but these are the most common that we can use in solving differential equation. The linearity property, the constant multiple, the first shifting theorem, the second shifting theorem, transform of derivatives, derivatives of the transform, and transform of integral. So I'll be focusing with these properties today, and then the application will be after the discussion of inverse Laplace transform. But I'll be giving you some examples on how we can apply the properties of Laplace transform. Linearity property. When we say linearity property, the Laplace of f1 of t plus f2 of t plus up to the n term, or fn of t, we can take actually the sum of the Laplace transform of the individual functions. That is the linearity property. The Laplace of f1 of t plus the Laplace of f2 of t plus up to the Laplace of fn of t. Okay? So to show, let us have the following example. Examples. Find the Laplace of the quantity 1 plus t cubed plus sine of 2t. Again, we can refer to the table of elementary functions that we have, so that you can find the Laplace transform of the different functions. So by linearity property, that is actually equal to the Laplace of 1 plus the Laplace of t plus the Laplace of t cubed plus the Laplace of sine of 2t. Okay? And we can have the individual Laplace transform of its function. So the Laplace of 1 is 1 over s plus, what is the Laplace of t? That is 1 over s squared. The Laplace of t cubed, using the formula of n factorial over s to the n plus 1. So that is 3 factorial over s to the 3 plus 1. And then the Laplace of sine of 2t. What is the Laplace of sine of omega t? That is omega over s squared plus omega squared. So therefore, you will have your omega here, which is 2. So that is 2 over s squared plus 4. Okay? So you may just simplify your answer. If you want, you can take the least common denominator of this, such as s squared, s to the fourth times s squared plus 4, and then you simplify. Or you make this part. This is 1 over s plus 1 over s squared plus 6 over s to the fourth plus 2 over s squared plus 4, and then make the necessary uh, simplification of your result. You can take your s to the fourth times s squared plus 4 and then do uh, the algebra. Okay? What about for the second problem? Find the Laplace of the hyperbolic sine of 3t. So that is again by linearity property, that is the Laplace of the hyperbolic sine of 3t plus the Laplace of t squared plus the Laplace of cosine of t. Okay? So again, what is the hyperbolic sine of 3t? That is 3 over s squared minus 9 plus 2 over s cubed plus for the cosine, you have s over s squared plus 1. And then again, you just simplify your result. That is your linearity property. So the values of the Laplace transform of the different functions involved were actually taken from the table that I showed you a while ago. Ito yung table ulit. Okay? Okay. Then we go to the next property, constant multiple. Actually, this is not presented in your module, the constant multiple, but this is also important. I just found this in one of the reference books. It is included as one of the property. What does it mean? If you have the Laplace of a constant times f of t, that is simply equal to the constant times the Laplace of f of t. For example, the Laplace of 5. Since there is no transform for 5, but what we have here is what? The Laplace of 5 is simply equal to 5 times the Laplace of 1. Since you have on the table the Laplace of 1. So this is equal to 5 times 1 over s, or simply equal to 5 over s. And then find the Laplace of 2t squared. So again, you do not have there your 2t squared, but the Laplace of 2t squared is simply equal to 2 times the Laplace of t squared, which is equal to your t squared is, the Laplace of that is 2 factorial over s cubed, or 2 over s cubed. So this is simply equal to 4 over s cubed. Okay? Then the next property is the so-called first shifting theorem. It is very important that we know the theorem, because we will just be uh, using the theorem for us to evaluate the Laplace transform of some elementary functions. Together with, for example, in this first shifting theorem, it is a multiplication of e to the at. So if the Laplace of the function is f of s when s is greater than a, then the Laplace of the product of e to the at and the function f of t would be equal to f of s minus a. That is, the substitution of s minus a for s in the transform corresponds to the multiplication of the original function by e to the at. What does it mean? Why is it called first shifting theorem? We are actually to shift s to s minus a in our f of s. But initially, if you have the Laplace of f of t, that is simply f of s. But if you are asked for the Laplace of the product of e to the at and f of t, you are to shift your s to s minus a. Let us see these examples. Find the Laplace transform of the following. So f of t is equal to e to the 2t times t cubed. Okay? So by first shifting, what you have to do first is to find the base. You have here your t cubed. This is your e to the at. So find first the Laplace of t cubed. What is the Laplace of t cubed? That is 3 factorial over s to the 3 plus 1, or that is simply equal to 6 over s to the 4th. That is if you are asked for the Laplace of t cubed. But since you are asked for the Laplace of e to the 2t times t cubed, as mentioned in the theorem, it would be equal to f of s minus a. So you are to shift your s here to s minus a. And which is a? This is your a, yung 2. You have e to the 80. So therefore, the Laplace of e to the 2t times t cubed would be equal to 6 over your s will be shifted to s minus a. S minus 2 to the 4. You just shifted s to s minus a. So if you want, you can expand this s minus 2 to the 4th. If in case you are given of multiple choice and you do not find 6 over s minus 2 to the 4th, then maybe you can expand this, and maybe one of the options will be the expanded form of this. Okay, so that is first shifting. You shifted s to s minus a. Now let us have the second one. So what is the base function that you are to find? So you have to find first yung Laplace of sine of 3t. So what is the Laplace of sine of 3t? From the table, you have 3 over s squared plus w squared, so plus 9. That is your Laplace of sine of 3t. But we are asked here for the Laplace of e to the negative 5t times sine of 3t. Therefore, you are to shift this s to s minus a, and our a here is negative 5. So therefore, the Laplace of e to the negative 5t sine of 3t would be 3 over, isi-shift natin si s into s minus minus 5, so s plus 5 squared plus 9. Or simply 3 over s squared plus 10s plus 25 plus 9, so plus 34. And that is the Laplace of the product of e to the negative 5t and sine of 3t. That is your first shifting theorem. Now we go to the second shifting theorem. If the Laplace of f of t is equal to f of s, and another function g of t is equal to f of t minus a when t is greater than a and 0 when t is less than a, then the Laplace of g of t would be equal to e to the negative as f of s. Okay, so we need to identify here what is the value of your a. So here you have t minus a. And again, we should know first the Laplace transform of the base function, f of t, which is equal to your f of s. And then after that, you multiply it with e to the negative as. Again, this is t minus a. So this is your value of a. So find the Laplace transform of this function of g of t. F of t minus 1 quantity squared when t is greater than 1 and 0 when t is less than 1. So in solving this, you are actually to disregard first your minus a. You have here your function of t minus a. So the base function would be f of t only. So you disregard yung minus a natin. So when you disregard this minus 1, what is our base function? So you need to find first the Laplace of t squared, which is equal to 2 over s cubed. Okay? And therefore, the Laplace of g of t would be equal to, based from this, would be e to the negative as. You have here your minus a, so a is 1. So that would be e to the negative s times the function of s. This is actually your f of s. F of s again is the Laplace transform of the function times your 2 over s cubed, or simply equal to 2 e to the negative s over s cubed. Okay? Another example. Find the Laplace transform of g of t in which your function of t minus 2 cubed when t is greater than 2 and 0 when t is less than 2. So what is the base function? So we need to find first your f of s, which is equal to the Laplace of, disregard natin yung minus a, so the Laplace of t cubed. What is the Laplace of t cubed? That is 3 factorial over s cubed plus 1, or this is simply 6 over s to the 4th. That is your f of s. And therefore, the Laplace of g of t would be equal to e to the negative as. Your a here is 2. So e to the negative 2s times your f of s, which is 6 over s to the 4th. And therefore, this is simply equal to 6 e to the negative 2s over s to the 4th. Okay, that is your second shifting theorem. Second shifting because we had the determination of the Laplace transform of the new function. So you have here two functions actually, your function of f of t and you have your g of t. That is the second shifting theorem. And now we go to the transform of derivatives. And this is actually what we are going to use later in the application or in the solution of differential equation using Laplace transform. So also in your module, the derivation for this equivalent of transform of derivatives are presented. So you can check why the Laplace of the first derivative of the function of t is equal to s times the Laplace of f of t minus f of 0. When we take the second derivative, so the Laplace of f double prime of t is equal to s squared Laplace of f of t minus s f of 0 minus f prime of 0. Then when you take the third derivative, the Laplace of f triple prime of t would be equal to s cubed, the Laplace of f of t, minus s squared f of 0 minus s f prime of 0 minus f double prime of 0. So if we are going to look at the trend of the Laplace transform of derivatives, as you can see, in the f triple prime of t, you have here s cubed. So whatever is the n value here, that would be also the power of s. And you look at the terms that you have your s cubed, then followed by s squared, then s to the 1, then s to the 0 is for the last term. And for the function, you have here Laplace of f of t on the first term, and then on the second term, you have f of 0, followed by f prime, up to the f double prime. So as you look here, f double prime is one order lower than what we are looking for or the order of the derivatives that what we are looking for. So therefore, if you take the general, the Laplace transform of the nth derivative or f to the n of t would be equal to, in terms of s, so s to the n, s to the n minus 1, s to the n minus 2, s to the n minus 3, up to s to the 0. And then you have s to the n Laplace of f of t minus s to the n minus 1 f of 0 minus s to the n f prime of 0 minus s to the n minus 3 f double prime of 0 up to the last term should be f to the n minus 1 of 0. That would be the general form of the transform of derivatives. So you need to identify or to uh, determine the function of 0 or the function when t is 0, the first derivative of the function when t is 0, etc. up to the n minus 1 derivative of the function when t is 0. And you just substitute here in the formula or equation for the transform of derivatives. Let us take this example. Evaluate Laplace of f prime f prime of t with f of 0 is equal to 1. So on our previous slide, again, when you have your first derivative, you have it, this one. So the Laplace of f prime of t is s, the Laplace of f of t minus f of 0. Okay? Sorry. I think I missed one given here. Let me check first for a while. There is a given f of s, where f of s, you are given of f of s here, which is equal to 1 over s minus 1. Okay? So from the Laplace transform of f prime of t, which is equal to s times the Laplace of f of t, which is again the Laplace of f of t is simply your f of s. So it is given minus f of 0. So this is simply equal to 1 over s minus 1, since again this Laplace of f of t is your f of s, minus f of 0, which is given to be 1. Okay, and simplifying, this would be your s minus 1. This is 1 minus s plus 1. Sorry. Given here is, yeah. So you have here your s, sorry. So you have here s times Laplace of f. So this is s times. Okay. So this is actually s. So s minus s. So this is equal to 1 over s minus 1. And then for sample problem number 2, evaluate the Laplace of f double prime of t with given f of 0 equals 1 and f prime of 0 to be equal to negative 1. So the Laplace of f double prime of t from the equation that I showed you is equal to s squared, the Laplace of f of t, or again, this is simply your f of s, but there's no given f of s this time, minus s times f of 0 minus f prime of 0. That is our formula for the second derivative. So you have here your s squared, and depending on the given function of f of t, so you can just have it f of s, which is equivalent to the Laplace of f of t, minus s, and then f of 0 is given to be 1, and our f prime of 0 is negative 1, so minus negative 1. And therefore, you have your Laplace transform of the second derivative as s squared times f of s minus s plus 1, depending on whatever function it is, or there are times, just like in example number 1, you are given already of the f of s, which is 1 over s minus 1. So that is the transform of derivative. So later, we will be using this in our application. That would be for next meeting after discussing Laplace transform. Then the next property is derivatives of the transform. Take note, the previous topic or the previous one is transform of derivatives. And here is the derivatives of the transform. In some other textbook or references about Laplace transform, this is also called the multiplication of powers of t. This is also known as multiplication of powers of t, but what is involved also is the derivative. That if f of s is equal to the Laplace of f of t, and n equals 1, 2, 3, then the Laplace of t to the n times f of t is equal to negative 1 to the n derivative of f of s with respect to s. Okay? So if you will find a function multiplied by powers of n, or simply t to the n, you are actually to find first the Laplace of the function of t, and then determine what is n. If it is first derivative, then you just take the first derivative of f of s to be multiplied to negative 1 to the n. If this is t cubed, then you have to take up to the third derivative of the function of s and multiply it with negative 1 cubed. So to illustrate, find the Laplace transform of f of t is equal to t sine of 3t. Again, the first thing that you have to determine is the Laplace of the base function, which is sine of 3t. What is the Laplace of sine of 3t? That is equal to 3 over s squared plus 9. Okay? And then, this is your f of s. And since we only have here times t, so the Laplace of t times sine of 3t, since n is equal to 1. So n is 1. So your f of s is 3 over s squared plus 9, and your n is equal to 1. So using this formula, therefore, the Laplace of t times sine of 3t would be equal to negative 1 to the 1, the derivative with respect to s of 3 over s squared plus 9. So you just need to take the first derivative of this. So what is the first derivative? So this is negative times derivative of the quotient. So s squared plus 9 times 0 minus 3 times the derivative of s squared plus 9 is 2s all over the square of the denominator s squared plus 9 square. So simplifying, the Laplace now of t sine of 3t would be equal to negative of negative. So you have 6s over s squared plus 9 quantity square. So depending on the value of n, if you have t squared, then you still need to take the second derivative. But do not forget the negative 1 to the n. Because if you have odd number of n, then you have to multiply it with negative 1. It's okay if n is positive, is even, I mean. You will just result to positive 1. But if it is n with odd number, then you have to multiply it with negative 1. Okay, so that is the derivatives of the transform. Again, very important is to find first the correct Laplace transform of the function. And then after that, you take the derivatives. The reason why it is termed as derivatives of the transform. But again, in some references, you will find this as the property in which it is titled as multiplication by powers of t. Because you can have t squared, or t to the n in general. Now, the last property is the transform of integral. If the Laplace of f of t is equal to f of s, then the Laplace of the integral of f of u du evaluated from 0 to t would be equal to f of s over s. Okay, so transform of integral. Let us take this example. The Laplace of u squared or the Laplace of the integral of u squared minus u plus e to the u du. So from this property, the Laplace of the integral from 0 to t of u squared minus u plus e to the u du. It is said that it is simply equal to f of s over s. So what you need to do is just to replace the u here by t. Okay, but you need not actually to integrate it because of this property. You are just to change your u to t, and then you take its Laplace transform. So that would be equal to the Laplace of the quantity. Just change u to t. So that would be t squared minus t plus e to the t. Okay? So this integral actually would be equal to this. You just change u to t, but do not integrate. Divided by, according to this, is your s. So our f of s actually is the Laplace transform of this. So you need to take the Laplace transform. So 1 over s times what is the Laplace transform of t squared. So by linearity property, that is the Laplace of t squared minus the Laplace of t plus the Laplace of e to the t. So this is equal to 1 over s, and then finding the transform of each function, that would be 2 over s cubed minus 1 over s squared for the Laplace of t. And what is the Laplace of e to the t? That is 1 over s minus 1 or s minus a from the table, wherein a is 1. Okay? And therefore, you can simplify. You can take so 1 over s times, you have here your s cubed times s minus 1. So you have 2s minus 2. Then you have minus s times s minus 1. Then you have plus s cubed. So this would be equal to 1 over s times 2s minus 2. Simplifying, you have 2s minus 2 minus, that would be s squared plus s cubed all over s cubed times s minus 1. That correct? And then simplifying, that would be s cubed. So minus s squared plus 3s minus 2 divided by s to the fourth times s minus 1. So you have this as your Laplace transform of this integral. So again, you have f of s over s. So what you need to find first is your f of s, in which your f of s, again, you just replace u by t. But do not integrate this, because the integral of f of u du, as mentioned, is simply equal to your f of s over s. So you just replace u to t and then take the Laplace transform of its function and you divide it by s. So simplifying, this is your result for the Laplace transform of the integral. S cubed minus s squared plus 3s minus 2 divided by s to the fourth times s minus 1.